Hi everyone. Let's talk about rotational motion. So we had seen in linear motion these parameters, we are familiar with them. So we measure distance, and then from the distance covered within a given amount of time, we can calculate velocity and acceleration, which is the change of velocity in time. So we have these formulas we used for different problems. For velocity, we have this. For distance, we have this. For one-dimensional motion. So in rotational motion, we have, instead of linear distance, we have angle. So when you rotate around the same point, you start from here and you come back to the same point, you basically do this rotational motion, right? So you're a little bit familiar with this concept. In uniform circular motion you have seen, it's like a specific version, specific kind of rotational motion. In there you have the speed that you rotate and the radius that you rotate around is constant. So then it becomes uniform circular motion. But in general rotational motion, you can change your speed, which is rotational speed, and you can change your radius. They're all like changeable variable, basically, parameters of the motion. So now we will be seeing more general rotational motion. So as I was saying, in linear motion, we measure distance in meters. Instead, in rotational motion, we measure angle. We show it with Greek letter theta. And the unit is, generally speaking, is used in radian. So when you complete one circle, it's called 2 pi radian in terms of radian unit. And generally, this is the one which is used in rotational motion mechanical problems. It's also 360 degrees, but degree is not used in this concept that much. Mostly radian is used. Sometimes revolution is used. This is more like a general daily life language, but I've seen questions with revolution as well, which corresponds to 360 degree or 2 pi radian. So all these three things corresponds to one full circle. So half of a circle is going to be then pi radian, quarter of a circle is going to be pi over 2 radian, which is then half a circle in degrees, 108 degree, or half a revolution. So these are like three different units that could be used for rotational motion problems. And again, mostly radian is used, and sometimes revolution is used because it's a daily life kind of unit. It's not really a real unit, but you're counting how many times the object is revolving around the center of rotation. So if you use the radian for the angle measurement, then the rotational velocity is going to be radian per second, and the rotational acceleration is going to be radian per second square. So again, the angle is shown with the lowercase theta in Greek alphabet. Again, lowercase omega is used for the rotational velocity. Like we measure in linear motion, linear velocity as distance over time. In rotational motion, we use angle over time instead of distance over time. That makes sense because it's rotational parameters basically replacing the linear parameters. And the same thing goes for the rotational acceleration. The unit is radian per second square, because basically it is, in linear motion, this is basically change of velocity in time. And so this is the change of angular velocity or rotational velocity in time. So instead of rotational, sometimes angular is used. So in this concept, you will hear either rotational velocity, rotational acceleration, or angular velocity or angular acceleration. So it's the same thing. They're interchangeable, basically. So what you do for these formulas that we have been using, that we have used for the linear one-dimensional motion, you replace the parameters of velocity with the rotational velocity or angular velocity, and the acceleration with rotational angular acceleration. So as you can see, the format of the equation is exactly the same. Only thing that you do is the change velocity to rotational velocity, acceleration to rotational acceleration. So the formulas, again, has the same form. The only thing that changes is from linear velocity, you change to angular velocity, from linear distance to rotational distance, which is angle. And acceleration-wise, also linear acceleration, angular rotational acceleration. So, but there is a relation between those parameters, because if you, let's say this was a running parkour that is circular, you go from point A to point B, so it means you're also running like a linear distance, right? There's a meter associated with this arc. Like, what is the linear distance from A to B is given by also it is related to the radius you're rotating around and the angle that you covered, and it's given. This is the relation basically from point A to point B. This is the linear distance of this arc, which can be given by radius of that circle times the theta that you covered from point A to B. And so radius is important because you can see that if you take a shorter radius, let's say halfway here, so even if you rotate the same angle, the linear distance of this is half, right? So that's why radius is important. If the radius is half, then the linear distance that you cover from point A to point B, in this case, it's going to be, I guess, C to D, is going to be half, even if the angle is the same. So that's why I draw here, trying to mimic, you know, the Olympic running competitions. If you ever see one, if you ever watched one, they start from different positions, not from the same line. Instead, if there are, let's say, three runners, one person, the innermost person, starts from one point, the outer person starts a little further, and then another one even more outer starts even further down the road. It's because of the fact that the radius of number one is, as you can see, is shorter than number two. If you just take this back here at the same level as one, you will see this much of this difference in the radius. And if you take number three here, it's even bigger. So there's a difference between the linear distance that they are going to be running around the center, right? So in order to compensate that, in order for them to run the same distance, same linear distance, they basically calculate what is the distance difference when they run around and come back to the same point. They just let these runners start from these positions because that's how they make sure that all these three runners run the same linear distance. I hope that clarifies that if it ever puzzled you. And because of this linear distance relation between the radius and the angle, and you know that the distance divided by time is equal to velocity. So if you basically apply to that here, like you divide both sides with time here, and then time here, radius is going to be constant, right? You get basically distance over time is velocity, linear velocity. Theta, angle divided by time, is angular rotational velocity. So you have this velocity relation between rotational and linear velocity. So these two basically equation is the relation between the linear and rotational distance and velocity. So there is one more thing that I want to talk about when you talk about linear corresponding to rotational is Newton's second law. So you know that total F is equal to ma. Newton's second law in linear sense is written like this: net force is equal to the total mass times the acceleration of that system. For the rotational motion, the generator of rotation, as we talked before, was torque, right? We show it with tau, and we used the formula in that lab, for example, as F, which is the perpendicular force, times the distance you apply that force around the center of rotation. This is basically really the formula for the torque. The force you apply, at what distance you're applying that force, creates this torque, right? But this is a relation between the force and the acceleration. The same thing happens for rotational motion. You have the rotational motion generator torque instead of force. And I'm going to write it and explain what I means now here. So similar relation between the rotational acceleration and torque exists. So this is basically Newton's second law in rotational motion. So, and again, Newton's second law is a relation between linear acceleration with the force that is applied onto the system. So Newton's second law in rotational motion is the relation between the rotational acceleration and the net torque. on that system that creates that acceleration. So here, what you don't know is that, you know what torque is, it's generator of rotation. You know what angular or rotational acceleration is, which is alpha. But you didn't come across with the I first. This is the first time, I guess, seeing this. So in Newton's second law, we talked about the fact that mass is kind of a resisting entity to the acceleration. So if you take two person and make them push a car, they might be able to push it, they might be able to accelerate it because the mass of the car is not such a big resisting quantity. In that sense, they can overcome that resistance. However, if you take the same two person and make them push a truck, they won't be able to do that. They won't be able to accelerate a truck because the mass of a truck is much bigger than a regular car. And so that resisting entity in the truck is too much to overcome for them. So you know that if the same force is applied onto a bigger object, you will get a smaller acceleration. That's why we call this mass as linear inertia. The same thing, same concept exists in rotational motion. We call it rotational inertia or angular inertia. And if you, I would like you to actually, if you haven't done this, you can basically attach a string around a small object in the house and try to rotate it at the end of that string. So the string length is going to be the radius of that rotation, right? So if you try to rotate an object of mass m at the end of a string and try to make the rotation at a smaller radius, just make the string shorter, hold it from a shorter end a little bit like this, and then rotate it at a shorter radius. You will see that it's harder to rotate at a longer radius. And of course, it's obvious that if you increase the mass, if you get a bigger object and try to rotate at the same radius, it is harder. So the resisting entity, the resisting parameter in rotation is not just the mass, but also the radius is important. So rotational inertia is a quantity we call I, we show it with a capital I, and it is, I'm going to say mathematically, mr square for a point particle, but there could be a constant in front, depends on the shape of the object. So rotating a rod, for example, you take a rod, a stick basically, try to rotate it one end of it is different than try to rotating it at the center of it. So how the mass is distributed around the center of rotation matters. So if you change the same mass, let's say this stick is 100 grams. Take 100 gram like a disc shape object, try to rotate it at the center. It's different. The resistance, let's say, to the rotational acceleration of this object is different than this object because mass is distributed around the center of rotation is differently. And that basically comes into play as a constant in front of here. And if you look at the book, you will see for different shapes like a disc, a sphere, like a ball, or a stick at one end, rotation around one end, or stick at the center of the stick, if you try to rotate it at the center of the stick, is different constants here. It's only equal to mr square for a point particle. If it has a two-dimensional, three-dimensional structure, there is going to be a constant here. So this part is the important part that we talked. The mass is important. Mass is a resisting quantity when you try to rotate the object, and also at what radius are you trying to rotate that object, also important. It comes as r square. So an mr square itself, so the constant is 1 for a point particle. For all other 2, 3-dimensional objects, there is going to be constant here. I'm not going to ask you to memorize them, but you're just going to be given, if there is a disk involved, I'm going to give you the constant, or if there is a stick involved, I'm going to give you the constant. So all I want you to know is that there is this correspondence for Newton's second law that was in linear motion in this form that turns into in this form in rotational motion. I hope this is going to help you to understand the rotational motion concept, and let me know if you have a question. Have a good day.